Welcome everybody in the lecture hall. Welcome everybody on Zoom. Welcome everybody from the future. Today we are hopefully going to finish this lecture on Spark, Apache Spark. I have two clicker questions to ask to make sure that you followed. And I would also like to take a bit of time at the beginning to answer any questions that you might have from last week. I will try to keep the pace not too fast to make sure that all of you are following. So what I think I will do is first I'll ask you the two clicker questions on MapReduce and Spark. Then I'll take any questions that you might have. So my first question is, what is an RDD? Because I used RDD all over the place today. Is it a resilient distributed data set? Or is it a recoverable distributed data set? Or is it a recoverable dividable data set? Or a resilient dividable data set? So let's have a look. Wow, 100%. People have been working this week. All right, so indeed, this is the correct answer. Resilient distributed data set. Distributed because it can be enormous. It can be petabytes worth of data, and it can be spread all over the cluster. It means it's partitioned, the same idea as files partitioned in blocks. Here we have a collection of whatever, a collection of values, partitions, and the partitions are spread all over the Apache Spark cluster. So this is for distributed. Resilient, because we'll see, I already showed you last week that the RDDs are basically nodes in some general DAG, in a distributed acyclic graph. And the reason is simple, is that we are basically computing RDDs. We are computing these collections, and every collection depends on one other collection or two other collections. And this is this dependency graph that you have, right? And this dependency graph can be as big as you want, right? You can have maybe a chain of 5 transformation with 6 RDDs. That's entirely possible. And resilient means that if we lose one along the way, because one machine crashes or we run out of memory or whatever, that's not a problem. We just recompute it. And if necessary, we'll even recompute all the way from the beginning, right? So this is what resilient actually means, right? So resilient distributed data set, but really on the logical level, think of it as a collection of values, a collection of whatever, right? This is what an RDD is. A collection of whatever that can be very, very large. So that was my first question. Let's see if you also nailed the second one. So we introduced, that was 2 weeks ago and the beginning of last week, the first version of MapReduce, right? In the very early days of MapReduce. And then we introduced Yarn in order to solve some of the problems of MapReduce. And that led to a second generation, a second version of MapReduce. So is it that map slots and reduce slots are statically assigned so that they are often idle and that doesn't fully use the cluster resources? Or when a MapReduce split spans over 2 HDFS blocks, there is a massive drop in performance because data must be streamed from another data node over the network, right? Does Yarn solve that? Or does it solve that there's a bottleneck on the job tracker which has to do both scheduling and monitoring, jack of all trades, master of none? Or map slots and reduce slots are statically assigned before the job starts, and that may lead to suboptimal numbers of reducers. Multiple answers are possible. So what issues does Yarn address and solve? So we have a majority with two of them that are quite popular. I see some changes of answers. Still have a chance. And the majority is correct on those two. And the fourth one, you could argue. I marked it as correct in the sense that the fact that you statically associate the slots puts constraints on the number of reducers you can have, right? Because the number of reducers, you need to book part of the cluster. In the first version of MapReduce, you need to say that part of the cluster does map and that part of the cluster does reduce. And during the mapping phase, the part of the cluster doing reduce does nothing. And during the reduce phase, the part of the cluster doing map does nothing, right? So that puts constraints. So this is why I also marked the last one as that could be true. The third one, this is true. The job tracker in the first version of MapReduce has too much to do. It both has to schedule the resources and allocate the slots to mapping and reducing and so on, but it also has to monitor for crashes and restarts if necessary and orchestrates the whole shuffling. So this is just too much. And indeed, Yarn solves that by delegating all of the monitoring to one of the worker nodes. It's no longer done on the coordinator node. It's done on one of the worker nodes. The first one is true. Also, this is what I told you, that you have statically, you know what it means statically, right? Statically means before the job starts. Before the job starts, you need to allocate part of the cluster to mapping and part of the cluster to reducing. That's what statically means, as opposed to runtime. Runtime is when it's actually ongoing, once you have launched the job, right? So this is true in general in computer science. There is the static part or compile time part before you actually run the program. And then there is the runtime part or dynamic part while you are running the program, right? And there are very interesting theoretical problems on the fact that when you try to do as much as possible statically in order to optimize, but you cannot do everything. And in particular, there is the halting problem that is basically trying to predict if a program is actually going to come to an end. This is impossible. It's undecidable. So this is this whole tension in computer science between compile time and runtime, between static and dynamic, right? And so in the case of MapReduce version 1, at compile time, we split the cluster into these two parts. But with Yarn, we switch it to the dynamic part, meaning that we first allocate the map slots, and we worry later dynamically about the reduced slots. Okay? The second statement in the middle is correct, but it has nothing to do with Yarn, right? The fact, I wouldn't call it massive though, but it is true that the splits, you remember that the splits in MapReduce, they divide between key value pairs, right? And that might not exactly correspond to where two blocks are separated, because for HDFS blocks, it's about bits, right? You look at zeros and ones and you cut wherever you have the end of a block. But in MapReduce, you need to be careful. You can only cut right after a key value. That might not exactly coincide with the blocks. And so there's a tiny part of it for the part of the last key value pair of every split that you need to read very often over the network, right? So this is a slight performance drop. Okay. So all of that we covered last week. Let me go back to the slides. Okay. So now I'm going to give some time for questions. Anything that wasn't clear, that you didn't understand on the whole of MapReduce, on what we did about Spark, anything you didn't understand that you would like me to repeat, knowing that you shouldn't be hesitating to ask questions, because if you didn't understand something, it's very likely somebody else and many other people didn't either, right? So you should really never hesitate to ask a question, right? There is no such thing as a stupid question. So do you have any question in the room, either that you prepared or spontaneously? on Zoom? Any questions? Giving you a bit of time. I'll ask questions then. I'll ask questions. So let me do some sort of FAQ from the previous years, the sort of questions that were commonly asked. One question was, when we talk about the second version of MapReduce, do we talk about Spark? And the answer is no. Spark is completely different. Spark is a different piece of technology. It's been developed by completely different people at Berkeley. And now there's a company that was founded called Databricks. Who heard of Databricks? Right? It's now a very large private company. And so they are the ones who basically, so it was spinned off from Berkeley, and so they developed Spark. Spark is open source, right? But they also have a proprietary distribution that they released. So Spark is not the same thing as the second version of MapReduce. In fact, what's the difference between the first and the second version of MapReduce? Well, from a user's perspective, none. There is absolutely no difference. Exactly the same thing. You have this mapping phase, you have the reuse phase, that's it. The only difference between the two is if you look down at the physical level very deep, then you see that the second version is using Yarn instead of the job tracker and task tracker. But from the user's perspective, there's absolutely no difference. Exactly the same interface, right? You might have, once in a while, they update the Java interface or the Java API, but that has nothing to do with the use of Yarn, right? So we have the first version of MapReduce with the job tracker and the task tracker, but it had all the issues that we mentioned here. We have the second version of MapReduce that looks exactly the same to the user, except that in the background we use Yarn, and some of the orchestration is delegated to one of the worker nodes instead of the coordination node. We don't have any job tracker and task tracker anymore in the second version of MapReduce. Instead, we have the application master of Yarn, and we have the containers that take care of the rest. And then we have Apache Spark, which is a new generation of massive parallel processing. So that was the first question. Again, a few seconds for you to ask questions. Otherwise, I'll continue to make up questions. Yes, go ahead. So let's give you, can I just try to read? Let me increase the volume so that people hear you, because there is some sort of noise otherwise, so I need to go ahead.
Check. I don't know. Can you hear me? Yeah, should work. Just like generally, how is it solved kind of storage-wise if you do this massive parallel processing on like the different blocks and so on? Especially then if we have like huge data processing parts and a lot of different tasks, which kind of only, if I understood it correct, get activated, like kind of it's saved, right? The task, and then you have to activate it, and then it like calculates all of it because it's sleeping until you actually activate it. So how does this work?
Mm-hmm. Are you referring to Spark or MapReduce? MapReduce maybe, right?
Probably yes.
Probably MapReduce.
Like still a bit messed up there.
Okay. So let me try to re-explain a bit all of this. So we are talking about the physical aspects, right? So again, with data independence, you need to separate between the logical aspects and the physical aspects. Logically, MapReduce is very simple. You have a collection of key value pairs. You apply a map function to every key value, and that produces intermediate key values. And then you group these intermediate key values by key, and then you apply a reduce function to every group that has the same key, and you get output value. That's the logical level. This one is relatively simple. Now, on the physical level, how do we make it happen? And this is where it's absolutely beautiful, because all of the physical part is completely hidden from the user, but it's very interesting. So you really need to consider the two stages one by one, because they do not work in the same way. The map phase, the first half of MapReduce, the map phase, is reading the data from HDFS. Let's say it could also be S3, it could also be Google Cloud Storage, Azure, but let's take HDFS. So in that case, the data is stored on HDFS in blocks all over the cluster, right? And what you try to do in the map phase is to say every block is kind of sort of corresponding to a task, right? I'm saying kind of sort of because there's this last few bits of the last key value pair that might spill over another block, but very roughly, a block gives you a task, right? So if you have a data set that has, let's say, 10,000 blocks, then you have 10,000 tasks. And a task is just a to-do. A task consists in evaluating the map function for every key value in a block. This is what a task is, right? Now, still in the map phase, this is the storage. Now, how do we execute it? Well, you know that when you have computers, you execute things with CPUs, right? Central processing units. That's the processors that you have in computers. So this is the brain of the computers. So when you need to take care of the tasks, you need to distribute the tasks over the CPUs, right? And more exactly, you need to distribute the tasks over the CPU cores, right? Because you know now that CPUs have multiple cores, right? In your laptops, you might have 8 cores, you might have 16 cores. That's advertised when you buy the computer. So it means that every one of these cores can handle one task at a time, right? So imagine that you have 1,000 cores available in your cluster. Maybe you have 100 machines with each 10 cores. Typically it's powers of 2, but to simplify, 100 machines with each 10 cores. So you have 1,000 cores. We call them slots, right? 1,000 slots. And what happens is that you take your 10,000 tasks, you take 1,000 of them, the first 1,000, and you put them all over the 1,000 slots. Every slot has one task. So at that moment, you have 1,000 tasks that are being executed. And the other 9,000 tasks, they are just waiting to be executed. They are just in the queue, right? So you start with the 1,000 tasks. And then in parallel, every one of these cores, every one of these slots is evaluating the map function, each of their own task, right? Each of their own HDFS block, and they are going through the evaluation of the map function, and they produce these intermediate key value pairs. Now, at some point, some of the slots are going to be finished with their task, but not all of them, right? Not all of them at the same time, right? You know how it is. You're going to the Mensa and you eat with your friends, and one of them is finished first, right? And the others are not finished yet. So what do you do when you're finished first? Well, you go get a refill, right? At least in the ETH Polymensa, you can get a refill. So this is exactly what the slots are actually doing. They are getting a refill. So when a core is finished with their task, they get another task, right? And they keep getting other tasks as long as tasks are available. As soon as a slot finishes their task, they just get another task and another task and another task, right? So very roughly speaking, if you have 10,000 tasks for 1,000 slots, 1,000 cores, then every core will, on average, get 10 tasks, right? Who is with me? All right, 10,000 tasks, 1,000 cores, 10 tasks per course. It's only on average, though, because you might have cores that are very fast or that were very lucky with easy key values that were easy to process. So maybe these will get 20 or 30 tasks. And maybe there is another core somewhere, maybe because it's less powerful, or maybe because it was unlucky and got a task that was more complex. Maybe it's only going to have 5 tasks, right? So one slot will process 5 tasks, while another one is going to process 30 tasks, right, in the same time. So this is all dynamic and very nicely organized. And then at some point, you run out of tasks. And so what happens at that point is that you're going to have slots that are done with their tasks. And since there are no other tasks pending, they just become idle and wait, right? Then at some point, all of the slots will be finished, right? And then that's the end of the map phase. All of the intermediate key values are now available. Now, in the simplest case, what it means with available means in the memory of the machines, right? You might have 100 machines in your cluster, and in the working memory, in the RAM of these machines, you have all your intermediate key values that are waiting to be shuffled, right? I'll come back to when there's not enough memory in a moment, but let's assume that there is enough memory. So you have all of your intermediate key values. They are all over the cluster in the memory of the machines, the working memory, so not on the disk, really in the working memory. And then we need the shuffling phase. So there is the part of the cluster, so the reduce slots are now going to download their key values, right? So all the key values, the keys are automatically mapped. I put something in the Moodle about that in the Moodle forum. There is a mathematical way of saying if you have, let's say, 20 reduced slots, 20 reduced tasks, you create a number of tasks, 20 reduced tasks, it means that you're going to take all the keys and distribute the keys over these 20 buckets, right? Every reduced task is a bucket, and you just arrange to distribute the intermediate key value keys again in these 20 buckets, but in a way that all the key values with the same key, they must be in the same bucket. That's the only constraint. Typically, it's done with hash functions, right? You put the key through some sort of a smoothie mixer, right? And you get some integer out, and it's deterministic. So the same key will always give you the same integer. You take that modulo 20, and that gives you the bucket in which it goes, right? So based on that, it's math. So everybody can do math. All the reduced slots can do math. So they compute, they know exactly what keys they are supposed to get based on that. And they are requesting from the map slots, please send me over the keys that I'm responsible of. For example, I will be responsible for task number 5. So I'm going to connect to every map slot and request all of the keys that if I put them in the smoothie mixer, give me 5, right? And then I get them from all the map slots. And then the reduce slots that is responsible for that reduce task is going to then call the reduce function. It keeps them nicely grouped by key, right? And then it calls the reduce function on every group and outputs key value pairs, the final output key value pairs. Now, for the reduce tasks, with the reduced slots, it's exactly the same idea, right? You might have, I don't know, 20 reduced tasks, and maybe you have 15 reduced slots. It means that there's 5 extra tasks that will be the second ones, right? So you start with 15 reduced tasks, and the other 5 will be taken by whoever is finished first, right? And then at some point, you're done. And for every task, you spit out an HDFS file. As soon as a reduce slot is done with a reduced task, it's the results, the output key value pairs are spit out to some HDFS file. So if you have 20 reduced tasks, you have at the end 20 files on HDFS in the same directory. Okay. Now, let me come back, rewind a bit, and come back to this pre-shuffling, right? When you have all the intermediate key values in memory before they are downloaded by the reduced slots. What happens if it doesn't fit in memory? Well, if it doesn't fit in memory, we can steal a technique from HBase. And you remember that in HBase, we also had key values, by the way, in HBase. When they didn't fit in memory in the mem store, remember the mem store in HBase? Right? Many of you. So the mem store, when it's full, what do? We flush. Yeah, you got it. So you flush. That's exactly what we do with MapReduce as well. If it's full, the memory is completely full of intermediate key value pairs, you just flush them to disk, right? That's okay. The exact format is kind of irrelevant. It's just a local file on the machine. It's probably a sequence file or something like that, but that's something internal, but it's basically spit to disk, right? And then when you have the memory full again, you flush again and so on and so on. And then at some point, you might have several files. So what do you do when you have too many files? What goes with flushing? You flush and then you merge, yes, and that's called? Merge would be a synonym, yeah, and the exact term would be? You reduce the size. It's not exactly the same thing as the reducer part of MapReduce. It starts with a C. Compact, yes, exactly. Compact is what I was looking for. So you flush and you compact. But all that flushing and compacting is really some hidden physical layer in the map slots, right? It's just some size management, right? It's the way, if the memory is full, you just use flushing and compaction to put that on disk. And then the only difference is that when the reduced slots are downloading the key values, then you will also get them from disk instead of getting them just from the memory, right? But that's really a physical detail just in case it doesn't fit in memory, right? Now, what I could add is this. What would be the ideal number of map tasks compared to map slots and the number of reduced tasks compared to reduced slots? I'm just going to give you a rule of thumb because people might have different ideas. For the mapping phase, something like 5 times or 10 times as many tasks as slots is kind of good, right? So for example, 10,000 tasks for 1,000 slots, that's kind of good numbers, right? Exactly the same number of tasks and slots, that's not good because then you're wasting resources because some of them will be finished earlier, right? So you want a multiple of that. You want maybe 5 or 10 times as many tasks as there are slots. So that's for the map phase. The reduce phase, here it's kind of funny because there are actually 2 numbers and they kind of drop from the sky for some reason and people just use these magic numbers. And it's one of 2 possibilities. I think, if I correctly remember, that one of them is 0.95 times the number of slots. So you have a tiny bit less reduced tasks than reduced slots. And the other one is 1.75 times. So for example, if you have 100 reduced slots, then you have 175 reduced tasks. I think these numbers just came from experience, like people played with the system and they realized that these are kind of good numbers, right? So you do either the one or the other. So 1.75 is my favorite because it's the idea that you have enough extra tasks to not waste resources because the reduced slots that are over, they will take some extra tasks. So it allows you to distribute a little bit while keeping the whole shuffling under control, right? Did I answer your question? It was a long answer, but it was an opportunity to rehearse on the whole orchestration, right? Right? Great. Zoom? Oh yes, maybe you can read it and I'll read as well. Can you read it? Maybe out loud at the same time? Let me do it then. Question, in the lesson, MapReduce had a sorting phase, but it is actually just binning to the reduce tasks as an answer on Moodle. So in the reduce tasks, do the key value pairs come sorted in arbitrary order? Or is this a difference between the first version of MapReduce and later version? So I can already say that's not about the first or second version of MapReduce. That has nothing to do with that. The idea of sorting, there are 2 things basically. There is sorting that is done on the map slots in order to basically keep the intermediate key value pairs sorted, which allows you to keep them grouped, right? Sorting implies grouping, right? If you sort by key value, then you're going to have all the key values with the same key. In the sorted list, they will be together, right? So it's kind of sieben Fliegen in einem Streich, oder? With the fairy tale. The idea is that at the end of the mapping phase, when you're done with the map task, you keep the intermediate key value pairs sorted, and at the same time, you use the hashes of the keys to group them by reduced task, right? So the map slots are going to prepare by reduced tasks, and within one I would call it a chunk of intermediate key value pairs corresponding to a reduced task, it's sorted, right? So you hash to distribute over the partitions, and you keep the key values nicely sorted. And then when the reduced slot downloads these intermediate key value pairs, they will be sorted. Of course, the reduced slot might download from 1,000 different places, so it will have to merge these, right? So it's going to have to merge all of these chunks into a single big sorted key value pairs list, right? And then when you call the reduce function, you just go down the sorted list, and since all the keys are together, you call the reduce function on every group. MapReduce allows you to control this. You can have control about the hash function and the way you put the keys in the bucket, in the reduce stack. You can control that. You can change the way it's done. You can also have control on the way you sort the key value pairs. So you can override the sorting and provide your own way to sort the key value pairs, right? These are really physical details, and I think it's really advanced users that are going to control this sorting. So now going back to your answer, so the sorting phase, so that's basically the shuffling phase, and the sorting is part of that shuffling, right? It's the idea that you sort the key value pairs, but it's really a combination of partitioning and sorting, right? You distribute over the reduce task, and within every partition, you sort the key values on the map slot, and then the reduce slots merge the sorted list into a single big sorted list for every reduce task. With binning, I assume binding, right? So binding, that would be the hashes. In the reduce tasks, do the key values pairs come sorted? Yes, every chunk from one map slot comes sorted, but you need to merge into a big sorted list for your reduce task. That would be the reduce slot that does that. In arbitrary order, no difference between the first and second version. I think this answers the whole question. Are you satisfied with the answer? Yes, all right. We also have a question above. Don't they compute the last tasks several times to try to save time? That's a very good question that I'll come back in the lecture called Performance at Large Scales. Indeed, in some cases, you might want to compute some tasks several times, and there are good reasons for that. But that I would like to keep for the optimization that's really advanced, this idea of duplicating the computations, right? So I just postpone. All right, any other question? Yes, go ahead.
One of the slots is empty. It sits idle. Why it wouldn't take off tasks from other slots? And is this because we do the shuffling before, so that we don't have this type of then arbitrary that the key value that they're not sorted anymore?
Mm-hmm. So I'll answer for the first and second version of MapReduce because it's not the same thing. So the first version of MapReduce, the slots doing the mapping and the reducing, that's decided in advance. So it means that the slots, the reduced slots, they have to remain idle for as long as the map phase is not over. When I say they have to remain idle, I only mean they cannot start reducing. However, the reduced slots could still start downloading, right? They could still start downloading the intermediate key value pairs that are already available in order to be a bit early. They just cannot start calling the reduce function yet, because they can only do that once all the map tasks are available, right? So it is true, and that's a partial answer to your question, that the reduce slots can start downloading intermediate key value pairs before the map phase is over, but the reduce phase really starts at the moment that the map phase is over, right? The reason is that when you merge the sorted list of intermediate key value pairs, you need all of them from all the map tasks before you can start reducing. So it means that for the first version of MapReduce, that's the only performance gain that you can have. It's to start downloading in advance, but apart from that, you remain idle, and indeed you have a waste of resources for this reason, which is why in the second version of MapReduce with Yarn, we basically allocate the map slots, but not yet the reduce slots, only map slots. So the map slots start working and working and working. And what happens is that after a while, once the application master, so that's the container that orchestrates the whole thing, At some point, the application master, I don't know when it's 80% completed or 90% completed, so when it nears the completion of the map task, the application master is going to start launching containers for the reduce slots. And that it does a bit before the map task is over. But this is dynamic, that's the new part, meaning you only do it towards the end of the map phase rather than at the beginning. And when you have these new containers that were launched to do the reducing, then they can also start to download early, right? So these new containers, now maybe a few minutes before it's completed, they start downloading the key value pairs. But again, in the second version of MapReduce, it's still the case that these reduce slots can only start calling the reduce function when all the map tasks are done. Does it answer your question? Okay, thank you. Any other questions? On Zoom? All right, you're welcome. Okay, so I really wanted to take that time to make sure that we walk through all of that, to make sure that it's crystal clear. Who has the feeling that now they have a better understanding or a more detailed understanding of what's going on with MapReduce? Okay, a lot of raised hands. And on Zoom, can you raise your hands if you have a better understanding? Okay, raise hands too, very good. Okay, so we took almost the entire first hour, but this is what I wanted. I really wanted to make sure that you're all following. And actually, I have good news for you, because now that you know how it works, you will see that on the physical level, Spark is not really very different. So that's very good news for you, because it was worth learning all of that. Spark is following exactly the same principles. It's just more general, which leads me to another question. How is Spark more general than MapReduce? It's more general in several ways. 3. The first way is that in MapReduce, you have collections of key value pairs. It has to be key values. For the input, for intermediate, for the output, it's all key values all over the place. For Spark, it doesn't have to be key value pairs. It can, but it doesn't have to. So this is why I say collections of whatever. And these collections of whatever are called RDD. Remember? RDD is the name we give in Spark. So RDDs are more generic than collections of key value pairs, because they can be collections of whatever you want. It can be collections of pairs, but it can also be collections of anything. That's the first way it's more generic. The second way it's more generic is that in Spark, you don't have to have a map phase and then a reduce phase with the shuffling in the middle. In Spark, you can have plenty of phases all over the place in a generic dependency way, right? You can have a map and a reduce, but you could also have a map followed by a map, followed by a map, followed by a reduce, followed by another map, followed by a reduce, and so on. So it's more generic. Not only that you can chain 10 or 20 transformations instead of just 2. Not only that, but you can even have a whole tree or a whole DAG, a whole directed acyclic graph of dependencies, because in Spark, you can even derive an RDD from several RDDs. You can join, you can do set operations, and so on. So that's the third way. It's more generic than MapReduce. In Spark, you not only have map and reduce, you have flat map, filter, count by value, group by, join, order, and so on and so on. You literally have probably 100 different transformations instead of just 2, right? So these are the 3 ways in which Spark is more general than MapReduce. So MapReduce then becomes a particular case of Spark, right? When the RDD is an RDD of key value pair, when you only have map and reduce, and you only have these 2 phases, a simple tree with 3 RDDs with map and reduce. That's the special case of Spark. Who is with me? All right. So then, technically what I explained to you, that's kind of the slides that are here, but it's a good way to, what did I do with the, I lost my, clicker. Oh, there it is. Yeah. Okay. So, right, MapReduce looks like this. Now you know exactly how it happens physically with the slots and the maps and, sorry, the slots and the tasks and so on. So this is the particular case of MapReduce where the blue rectangles are the collections of key value pairs. In Spark, these would be RDDs. And then in Spark, we would have a map transformation and a reduced transformation. But again, in Spark, it's more general. You can have general graphs like this, where every rectangle is again an RDD, a collection of whatever. And then the arrows show you the transformations. And you see that it's a directed acyclic graph. It's basically any graph that doesn't go in cycles. If you follow the edges, following the pointers, you can never come back to where you were. You cannot cycle, basically. That's the only thing that's forbidden in there. It's also called the dependency graph. If we have physicists and you think of causal orders, that's kind of also what you get in special relativity, right? Okay. And these are all RDDs. That's what I told you. Everything here is an RDD, and an RDD is a collection of whatever. That's the logical way. Now, the next thing that I might not have told you, but when you type code in Python that builds that graph, in fact, nothing's happening on the cluster, absolutely nothing. It's going to start happening when you call an action right there at the end. The moment you trigger the action, then it starts computing and computing and computing, right? So that's called a lazy execution. If you don't have any action, then you don't do anything. The moment you trigger the action, then it starts, the cluster starts moving and the computing stuff, right? And I'll drive you through that. Okay. Now there are many ways to use Spark. Actually, in the same way, there's many ways to use MapReduce. One way is to use Java or Scala, right? Spark is actually written in Scala, but you know that Scala runs on the same system as Java, on the same virtual machine. So it's all written in Scala. So you can use the Java or Scala API, right? And I'll show you how it looks like. But there is also Python. Python, you have to know, is a bit slower because it's not the natural language of Spark. You can use it. It's very popular. It's called PySpark if you want to use Python. But again, you need to keep in mind that it's less efficient because there is a bit of overhead in the communication. The way you use these languages, you have a choice. You can either open what's called a shell. You open a command line window and you type live in an interactive way, Python or Scala or whatever, in the shell, and you immediately see the consequence of what you do. Or the alternative is that you write a very complex piece of software in Python or in Scala that basically creates a Spark job, and then you execute that application, right? Then it's not interactive because you first write the code and then you execute your code. So either the shell or the application. For whom is that clear? All right. So either live or write the whole code and execute the application. So right before the break, just so you get a feeling, I chose Python for this course because I think it's kind of the language of the moment, right? In 10 years, there will be another one, but for now, we do that. At the exam also, we'll have PySpark. So here's how it works. SC, so there is a bit of paperwork first, but that's something you don't need to learn by heart because it will all be, especially in the exercise and exams, you just need to click on the Jupyter notebook to execute that. But basically, you'll get some object called SC, and SC is the Spark context. This is what you use in order to create RDDs and so on. So sc.parallelize basically takes a list, so that's a Python list, a local list on your machine, and parallelize turns it into an RDD. So if you have a list of strings, parallelize turns it into an RDD of strings. Technically, it's the identity function. It doesn't modify the data, but what it does modify is that it ships it over the cluster rather than just being on your local machine, right? Okay. So that's creating an RDD. We store it in Python variable RDD1. That's a Python variable. Then we take RDD1 and we apply a transformation. I picked flat map. There's many others. So let's apply a flat map transformation to RDD1. And inside, there is that's called the lambda. It's really just a function. That's basically the equivalent of the map function and the reduce function, right? So if I do a flat map, I need to say how I want to map. So what the lambda means is that every value coming from the input is split, means we take the spaces and every space we split. So we have hello, comma, and then world, and then hello, comma, and then there, right? So you see what's happening in the middle. So we we associate every string with a split string. Lambda is just a fancy term. It's called lambda calculus. For those who know a little bit of this, it's a way of embedding a function inside a computer program, and that's just called lambda, right? So this is value, that would be your x, right? F of x, when you have a function in mathematics, f of x. So you have x right here, and here you have the definition of f of x. But since x is called value, then obviously that depends on value, right? So every value from the input, for example, hello world, is split into multiple values here, and that would be hello and world for here. And then if you apply that lambda hello there, you get hello and there. And then it's a flat map, so you flatten everything, right? Now you no longer know what came from where. Now you end up with 4 strings. Who is with me? So this is what flat map is doing. It's just cutting the strings based on the spaces. And this is a Python thing, right? What's happening here is just a Python function call that takes a string and outputs a list of strings containing all the string components. All right, then flat map, and we get that. I put here lazily evaluated because I put that in here for pedagogical purposes. However, the moment you type that in a shell, actually you can open a PySpark shell and type exactly that. In fact, when you type that and press enter right here, what's going to happen is nothing. Nothing at all. It's only going to tell you, yes, fine, RDD2 is an RDD. You know, big deal. So the thing is, at that point, nothing is triggered. However, if you call, that's called an action, count by value, then this triggers the whole computation. This, then suddenly everything is computed. So now I removed the lazily evaluated. Now it's actually going on. Count by value just counts the number of occurrences. So hello comma appears twice. So it says there's 2 of it, and then there, and then world, right? In fact, it's kind of a reduce-like mechanism, right? You could do it with map reduce as well, right? So that would be map, and that would be reduce. For whom is that clear? So that's a very simple example of what you can do with Spark, with Python in that case, and that's something you can run in the shell or in, oh, by the way, I forgot to say, it doesn't have to be a shell, it can also simply be Jupyter Notebooks, right? Jupyter Notebooks kinds of act as a shell. All right, so now we are going to take a break, but basically what will happen after the break is that I'm going to show you the entire restaurant menu a la carte of all the transformations. Flat map count by value are only 2 of them, but there's 100 different transformations and actions. So I'm just going to drive you through them, and you will see it's almost a walk in the park, very visual, all the kinds of transformations you can have. So have a good break. I took 4 more minutes, so we are going to start again at 9 for the second part. Thank you.